I want to just recap, because I think I missed a few important points that I probably didn't stress on. So I will just go through the main points for the free particle. Okay. So what we saw is that a general solution for a free particle wave function for a given wave constant k, psi k, is can be generally written as a linear combination of two exponential quantities, which represent just normal waves, oscillating waves. Okay, and these waves are associated with a velocity which is given by omega by k, and this is called the phase velocity. Okay, so if we consider this to be the wave function for a free electron which is moving in a certain direction, then what happens is that this phase velocity is found to be half of the classical velocity. Now that is a contradiction, because there should be some correspondence with classical physics. Okay, so then what we did was we constructed a physical wave function out of these stationary state wave functions. So what happens is that when you solve a differential equation, you end up with many solutions, and then some solutions represent the system that you are describing, while others are mathematical solutions but have to be discarded for some reason or the other. So in our case, these states, they turn out to be to have like the wrong velocity, and also they cannot be normalized to unity. Okay, because if you integrate this psi k star psi, you end up with infinity. So this wave function is not normalizable. So which means that, and this is also one of the postulates of quantum mechanics, that only normalizable solutions of the Schrödinger equation are physical solutions. So this cannot be the physical solution. And how did we arrive at this solution? We used the separation of variables. So the conclusion is that when you find solutions of the form of using the technique of separation of variables, where the position and time are factored out, then the solutions you get are not physical. Luckily, these form a basis, and we can form a superposition of these states, or take a linear combination of these states, and that represents my free particle accurately. So if you construct a propagating wave packet by using the superposition principle, using these states as a basis, you get a particle. And if you find the average value of the velocity, that is the group velocity of this wave packet, then this turns out to be the classical velocity. So you can, and this wave function also can be normalized. So we will look at that a little bit in the next few points. So here we are trying to normalize this one of the solutions, and you see that you have an integral of a constant, because these two terms, psi star and psi, they cancel each other, and you end up with infinity. Okay. So the main point here is that a free particle cannot exist in a stationary state. So a stationary state is characterized by the wave functions where the position and time are two factors. Okay. And this also means that there is no such thing as a free particle with a definite energy. Because you see, each of these wave functions that you obtain as a solution of the Schrödinger equation, they are stationary states and are associated with a definite energy. This will become clear when we go on to the particle in a one-dimensional infinite well. That what we mean by where you can actually have a particle which has a definite energy. Here you don't. So, and this is also true conceptually, because you see, when a free particle is moving, then unless you know the so let's say, how to put it. So if there is a moving particle, then classically you say that it has the kinetic energy half mv square. But that entails that you can measure its momentum accurately. But if you cannot, then of course it cannot have a definite energy either. So that is the problem with this free particle solution. So the superposition state does not have a definite energy, and neither does an actual quantum free particle. Okay, and how do you determine the classical velocity here? So the phase velocity is the velocity of each component of the wave packet. So this is omega by k, and this can be written as h omega by hk, so E by P. E is classically half mv squared. So both are classical velocities. So I can, CL. It's also CL. Missed that here. Oh, I cannot write on this. Okay, I missed the CL. So these are the two classical velocities. So you see that it is half the classical velocity. And the group velocity from wave physics is d omega dk. Now what we are trying to do is, we are trying to represent a classical free particle which is almost localized in space. So this, and it has an almost definite kinetic energy which corresponds to a wave constant that varies a little bit around k0. So there is a sharp peak at k0 for the wave constant of this wave packet. So this is necessary for the wave packet to be localized. And assuming that we are dealing with a localized particle, we can expand the function. So we can expand the wave constant about k0. So I mentioned this also in the last class, that we can find the actual coefficients of the superposition state of the free particle by expanding the wave constant about a certain value. I want to clarify that you can only do this when you want to describe a more or less classical particle. Okay, then you expand the k around k0, and then you can get to the wave function. And you can also try to evaluate then the group velocity at that point, so at the peak or the maxima of the wave packet. Okay, so and how do you do that? So we used this, or we defined this relation. If you remember that k square is related to the energy of the wave, and then we can rewrite this for the energy expression, then relating it with some angular velocity omega. We have h cross omega h square k square by 2m, and then we can find out omega is a function of k. So this is the expression for a free particle that we have obtained here. But whenever you have a function of the angular velocity in terms of k, or the wave constant, this is called a dispersion relation. You will encounter this in other fields of physics as well. So this expression is called a dispersion relation, and it can have different forms. For our free particle, it looks like this. And then you can evaluate this d omega dk. Okay, so when you do that, that is simple enough, and you put k0, and then k0 corresponds to this peak of the wave packet, and this corresponds to the momentum for that peak, and then you have the classical velocity. So this is so then for a quantum description of a free particle that is behaving sort of like a particle, then the group velocity can be identified with the classical velocity. Okay, and k0 can be identified as the average wave number of the wave packet, and p0 as the average momentum. So we have only deviated a little bit from the physical reality of the classical wave packet. So it's just that the averages are still the classical values, but there is a little bit of uncertainty around it in this situation. Okay, and so if you remember in the last class, we had a expansion for the superposition state, which was an integral of the various stationary state functions with some coefficients. And because it is a continuous distribution, you have a integral, and it's also just a function instead of a sum over some coefficients. And this function fk also peaks at this same value k0. So this is another way of thinking of what k0 is. So even fk has a peak at k0. So the wave packet is dominated by at least one stationary state function. There is a dominant function and there are some contributions from a fewer other functions. And then this describes a localized wave packet. Okay. However, it does not mean that that this is the only superposition state possible. So, so when an electron appears to behave approximately classically, you can make this assumption of expanding about K0 and a peak at K0, and you get a quantum description of a classical particle. But in principle, this electron could also exist in some superposition state, which is nothing like a classical free particle. Okay, so you can have maybe multiple peaks, okay, or you can also have something that is entirely delocalized. Okay, and if we go back to the Young's double slit experiment that we spoke about maybe in the first or second class, then you can now explain it somewhat. So the experiment was as follows. So there is a normal Young's double slit setup, and the electrons are sent one at a time through this double slit. Okay, and you detect it on a screen. So at a time, there is only one electron which goes through the slits. And when you observe many electrons, one after the other, and and look at the distribution of the electrons on the screen, it shows an interference pattern which is identical to the pattern one gets when one hits this double slit with a swarm of electrons. This was very strange, because how do you get an interference pattern when there is only one electron that is moving at a time? And then the next electron is released only after the other has hit the screen. So there is no way that they are interfering one with the other. So in terms of this idea of the superposition state and the fact that the free electron can have a superposition state which is entirely delocalized, you can explain this. So how will we think of this? So when we have one electron which travels to the double slit, okay, then the two slits are so close that they lie within the wave packet length. If you can speak of something like this, the distribution of the wave packet, like how long it is, the slits are closer than this. So basically, there is some finite probability of the electron going through either slit 1 or slit 2, or in this case, if you think if it is in a wave picture, it will just go through both. Okay. So, and to explain the interference pattern, this is what you have to accept, that this wave packet splits into two and goes through both as a normal wave front would. So if you remember the interference Young's double slit experiment for ordinary waves, the wave front hits the double slit and splits into two, and then the slits act as if they are two new sources, and again there are wave fronts which interfere with each other. Then the same thing happens for the wave packet. It splits in two, it passes through the two slits, and the two new waves generated, they interfere with each other and create a superposition state which has a probability distribution which corresponds to the interference pattern. Because the two waves from the two slits, they interfere and create this new superposition state. Then when this superposition state hits the screen, then again this collapses to one or the other state. So the electron, one or the other Eigen state, you can say. So the electron is found at different positions on the screen. Each time there is an electron going through. However, since the superposition state tells us the probability of the electron hitting the screen at different points, then over many experiments, so many electrons hitting the screen, you reconstruct the interference pattern. Okay, so this is sort of the experiment which verifies the fact that electrons can exist in superposition states, and this created the most strange, the strange result from quantum mechanics was this experiment, because if you So there are many steps where it is counterintuitive. So for one thing, I was thinking that maybe the question arises in some of your minds as well, that what happens to the mass of the electron? So when an electron or a wave packet is splitting into two and going through two slits, is the mass also splitting into two? Now the thing is that in quantum mechanics, mass does not have a fundamental role. It is the momentum, and momentum can split into two. Just like the momentum of waves can split into two, they can add whatever. And mass is a derived quantity from this momentum because we want to ascribe classical properties to the particle. So basically, you shouldn't be thinking of mass at all, because if you try to assign classical quantities to quantum mechanics, it creates more confusion than it solves problems. Okay, in fact, even Schrödinger was confused by this, and he had proposed that perhaps instead of a single particulate mass, maybe waves have a matter waves have a mass distribution which spreads along with the wave, and he tried to explain wave functions in this way, but he did not carry through all the conclusions, and finally just the probability density picture was accepted finally in the famous Copenhagen interpretation that you have heard before in this course. Okay, so here we will end the most strange application of quantum mechanics, like the thing which requires many angles of thinking, and we will suddenly go to something very simple. Okay, maybe I pause here and ask you if you have any questions, maybe from last class or from this class. Is there any question? If not, you can always email me or write on VLearn. I prefer you writing on VLearn, and I'm sure you will post this before the test. Yeah.
Ma'am, in your part, which we saw before, there was a sort of a distribution of energy, right? Which you had told us, like, which was the failure of classical mechanics.
Failure of classical mechanics in which experiment or?
Ma'am, the Wayne's law where we studied.
Wayne's law, yeah.
So, is there a sort of mass distribution like defined here, like, or is it can't be determined?
Where was the mass in Wayne's law? I mean, there it was just radiation.
Yeah, like they defined the distribution in the form of the exponent, right? And like it does not fail quantum mechanical model.
Yeah. Okay, yeah. They discretized the energy levels and said they are multiple of hν.
Yeah. So, ma'am, is there anything like quantifies this distribution, this mass distribution or the momentum within a wave packet?
Okay, so it depends on the situation. So for the free electron, there is no quantization of momentum. It is a continuous distribution and it can take any value. So all the valid solutions of the Schrödinger equation, they are eigenfunctions of the momentum operator. So the superposition state is an eigenfunction of the momentum operator.
So, ma'am, then individually it can be found out with that with the probability squared value.
Yeah, so what you're talking about is what Schrödinger was probably thinking about. I'm not sure exactly how he reasoned it, but maybe this was it, that according to the probability amplitude, the mass also splits among the components.
Like that so is there any defined relationship between the probability amplitude and the mass distribution, like proportional or something?
So you see, mass is coming from the correspondence with classical mechanics. So it is P is always mv. That is the classical expression, and that is what is used here as well. So if you know the momentum of a wave and you want the mass of the particle, then you have to know the velocity, and then you can do P by V and you can get mass. So that is how you do it. The mass is so from the wave function you extract the momentum. From the momentum you get the mass if you want it. But since you also need the velocity, which you can't get separately, then usually the classical mass you will see for the hydrogen atom, etc. You will just put in the classical mass. But this is but it is a derived quantity. So the wave function doesn't tell you the mass in any way. You put the mass into the Hamiltonian for your own convenience, and you keep it as a constant there. So it is. So you're not treating the mass like in a quantum mechanical sense in any way. It just acts like a constant in all the equations where you see it. And for a free electron wave function where you don't see it, no, actually you also see it. We have also put in the mass of the electron into the kinetic energy operator. Like it's a minus h cross squared by 2m, right? But this is just treated as a constant. And in the quantum picture, you can't think of anything happening to the mass. That is the problem. So I don't know how best to explain it. So this is the way. Let's see how to put it. So quantum mechanics does not tell you anything about the mass. If you need the mass to describe either the potential or if you want to describe the Hamiltonian and you put in a mass, that is up to you. Okay. Yeah, I'm not sure I can make you understand this very simply. So what I can tell you, which might help, is that if you go on to electrodynamics even later, then you actually can generate the mass of a particle in terms of quantum mechanical expressions. So there is a way of doing this, but it is not part of the quantum mechanics that we start out with. So it requires even more advanced methods, and it's also not standardized. So it's still in research phase. Okay, and I think it's best just to consider the mass as a constant that I use to define my Hamiltonian. Okay, if I don't need it, then I don't need it. If I need it, then I put it in. But quantum mechanics tells me nothing about what happens to the mass. It only tells me about the momentum. That is the thing. Okay, any more questions? Okay, if not, we will go on to the
We have
particle.
an average value for energy too, like P naught and V naught.
Yes,
like,
we have an average value for energy as well, and that
like
is
in classical terms.
That is the classical term, yeah. The kinetic energy, half mv square.
Okay.
Yeah. Okay. Now we will do something very simple. We will constrain this free particle with two infinite potentials at 0 and a. So the particle can only move in one dimension. So it is forced to move along, let's say, the x-axis between 0 and a. And these are infinite potential walls which it cannot cross. And we will suddenly see that things become much simpler then. Okay. Now, how to define this potential? So it's infinity outside the boxes, and when x lies between 0 and a, we say that Vx is 0. Okay. So the value 0 is just for simplicity. Okay. And now we have something that we didn't have before. We have some boundary conditions to help us solve the differential equation. So we know something more about the wave function. We know that it must be 0 for x less equal to 0, and it must be 0 again for x greater equal to a. Okay. And as before, we will solve. So what did we see? We found that if we want to solve the full Schrodinger equation, it is enough to solve the time-independent Schrodinger equation for the position part of the wave function, and the time part for the stationary states can simply be tagged onto this, because it does not change with the Hamiltonian. It is the same for all kinds of systems. Okay, so we will only solve the time-independent Schrodinger equation. And so in here, the particle has two energies: the kinetic energy, because it is moving, and the potential energy, which is defined by this set of relations. Okay, the kinetic energy operator is as before, and the potential operator is simply multiplicative, and it is 0. Okay, so we end up again with something that looks same as for the free particle, but we know that it is for this particular confined potential, and that is a potential V equal to 0, and this is a solution only between 0 and A. Okay, at this point, so I moved the h square by 2m to the right. Okay, and now I want to find out something about this constant. So from this relation, we know somehow that E is positive. So how do we know that E must be positive? So consider this, that if you have even the plus V over here, we have substituted 0 here, but let's say we have plus V. Then I can have take the V to the right, and I have a quantity which looks like E minus V minimum. Okay, so here you have E minus V. Okay, or we have E, not V minimum, but E minus V. Okay, and it can be shown that if E is greater than the minimum value of the potential in the Hamiltonian for every normalizable solution to the time-independent Schrodinger equation, so it must be greater than V minimum. So E must be greater than V minimum, and in our case, V minimum is 0, so E must be positive. So how can we see that? So if we take the V to the right, then we have E minus V over here, and if E is always greater than V, then E minus V is negative, and then this quantity is positive. So the second derivative of the wave function and the wave function always have the same sign. And if the second derivative and psi have the same sign, then the situation is somewhat like this. So what is this? So when psi is positive, then d squared psi dx square is also positive, and you get this curve. Okay? And if you have psi as negative, then d squared psi dx square is also negative, and you have this curve. Oh wait, let me see. Did I say something in reverse? I think I said something in reverse. So there is E minus V over here. Okay. So if E is ever less, okay, sorry, I said the argument wrong. So if E is ever less than V minimum, then there will be a point where this quantity is negative, then this is positive, and you will have psi's which look like this. I think I said if E is greater than V minimum, then you will then this quantity will become negative. That is of course wrong. So if E is by chance less than V minimum, okay, then this quantity is negative, so this whole quantity is positive. Then the second derivative and psi have the same sign, okay, and then the two possibilities are psi positive, second derivative positive, this one, psi negative, second derivative negative, this one, okay, and then you can see that these psi's will become larger and larger as x goes to plus infinity or minus infinity. So an integral of psi over x will never be a finite quantity. It will end up being infinite. So one basic requirement for any psi to be normalizable is that it dies out at large values of x. So as x tends to infinity, the psi's die out. That is a common trait for psi's to be normalizable. And if E is ever less than V minimum, then the psi's turn out to be not normalizable. And then those are not valid solutions to the Schrodinger equation. So we will simply stick to E greater than 0 solutions here. And how do we ensure this? We ensure this by replacing this quantity with k squared. Okay. So here there is the implicit assumption that we only want solutions where E is greater than 0. And this is again this classical harmonic equation solution, harmonic oscillator equation, and we know the solutions as before. That it is a sine kx plus b cos kx, where k is again root of 2me by h cross. And now we have some extra information, the boundary conditions, so we can try to find out a and b. So putting psi 0 equal to 0, it is easy to see. So this term becomes 0, then cos 0, 1, so b equal to 0. And psi a also 0, and and b 0, so this term goes away. We have a sine ka equal to 0. So from here, it is either a equal to 0 or sine ka equal to 0. If a equal to 0, then psi x is simply 0, which is a trivial solution. So that is not what we want. And if sine ka is equal to 0, then 0 is sine n pi and ka equal to n pi. And n can be 0 plus minus 1 plus minus 2, whatever. Now again, if n is 0, then again my psi x is 0. So n cannot be 0 for our particular case. And if n is less than 0, then you simply have the same wave function with a negative sign. So that is no additional information. So we just throw away the negative solutions as well. And it is sufficient for us to have n equal to only the positive integers 1, 2, 3, 4. Okay. Strangely, one of our boundary conditions gave us restrictions on the wave constant. So here we have sort of discretized the allowed wave constants. So unlike the free particle, you do not have a continuous distribution for the wave vector, wave constant or wave vector. You can only have certain discrete values. Okay, and this also means that the energy which is given by given as an expression in k, this also turns out to be discrete. So this is a very distinct feature of the particle in a one-dimensional box, that you have discretized energy values, unlike the free particle which has a continuous energy distribution. Okay. And this simply comes from one of the boundary conditions, that you force the wave function to disappear at a certain point. But A still remains to be found, and we have one more tool in our hand, the normalization constant. So if we want to find out only the normalizable wave functions, I set my integral to 1 and I find out the value of A from this. So what have we done? So our psi looks like, so psi looks like this. So, and this B is gone. So A sine kx. So mod A squared sine squared kx. So why am I writing it as mod A squared and not just A squared? Because A can in principle is in general a complex number. Okay, so that's why I write mod A squared, and then sine squared kx. Take a half common, 1 minus cos 2x, blah blah blah. Put in the limits. Okay, and you get mod A squared equal to 2 by A. So mod A is now either plus root 2 by A or minus root 2 by A. Since this sign on the wave function does not have much of significance, recall that we also ignored n values which are negative. So we're just sticking to positive solutions, and we choose root of 2 by a. I will tell you what would happen if we had taken the negative one later. So we take the positive one and we get our solution for the psi states. So we have also ended up with something very unique, the value n, which tells us which wave functions are allowed, which energies are allowed, etc. So this is a quantum number. So n can be called a quantum number, which quantizes both momentum and hence energy. And this is the quantized energy state. Okay. So what are the features that we can uncover from this wave function? So let's look at this. So like I said, there is a discrete energy spectrum. There is no limit on the value of n, so there are infinitely many states. The solutions are alternately even and odd. I forgot to draw the picture here. I drew it later, so I will explain that in a minute. Also, the number of nodes I will explain in a minute because I forgot to draw the picture here. And then the various eigenstates are mutually orthogonal. So we can prove this, of course. So if we have two psi's, one for n and one for m, and if we calculate this integral, this is called an overlap integral. And if we show that this is 0, then it means that the two functions are orthogonal. Okay? So if I have psi m and psi n, so I have psi m star psi n, then I solve this, okay? And I get, after putting all the limits, I get this expression. And what happens here? So how do I know that this is 0? So m and n are integers. So m minus n and m plus n are also integers. Okay. And m is not equal to n also. So this is also finite. And then we have an integral multiple of pi as the argument to the sine function. So this term is 0, this term is 0. So my integral is 0. Okay. So what happens if m is equal to n? So basically this argument fails because you have an m minus n at the bottom, and this term blows up. So you don't have a reasonable result from it. But anyhow, that was not our goal. Our goal was to show that the very different eigenstates are mutually orthogonal, which we have proved. Okay. Also, this set of eigenfunctions, they form a complete set. Okay. This proof has a very mathematical basis, and I have never done it, and I will not present it to you either because I don't know it either. So anyway, but you can sort of guess it is a complete set because if you use these wave functions as a basis for expanding a general function, then you see that they look like the Fourier expansion series. And you know that any function can be written as a Fourier expansion series. So if you accept the Fourier expansion series, you can accept easily that these eigenfunctions form a complete set. And then finally, if we want to tag on the time part of the wave function, we can simply put this factor for each energy eigenstate onto each of the psi functions, and you get the time variation of each individual eigenstate. Okay. And if you want, so this is for the eigenstates, and if you want the general time dependent function, so not one of the eigenstates, then again you can write it as a linear combination of these functions. And psi xt is then, this is the superposition state if you want one for a particle in a one-dimensional box. But okay, of course, whenever you have a superposition state, it always remains a question: how will you find out Cn? And to find out Cn, what you need is basically an initial wave function. So if you know an initial wave function, you can find out how this wave function changes with time at every space point x. Okay? So so knowing psi x is 0, is there a way to find out the coefficients Cn and thus psi xt? So let's say this is the first superposition state, my initial state, and I know the Cn's here. Then, so I know this function, okay? And then this can be also written as a superposition state of the various eigenstates. And to find out any so one of the CMs for this xt, you simply project psi with this, okay, and with this function. And because all the eigen states are orthogonal, then the overlap of psi n is a delta function, and you can find out the coefficients. Okay, fine. So knowing the initial wave function, you can find out then the coefficients of any general superposition state, which you can construct from the eigenstates of the particle in 1D box. Okay, now I have drawn the picture here, so I will tell you what is meant by functions that are even, odd, and also the what was the other thing that I said I will say later? Oh, the nodes. Yeah. Okay. So here what I have done is, so this is the box from 0 to A, and this is X, and I have the various energy levels E. So for n equal to 1, 2, 3, 4, I have drawn 4 wave functions. So you look at the form of this function, n pi x by A. And for various values of x, then you can, and you know n, let's say for n equal to 1, for various values of x, you can find the value of psi x and you can plot it. So what is the easiest way of plotting this? So you find the points where n pi x by A are odd multiples of pi by 2. So then these points will give me the maximum or minimum. So sine of n pi, whatever, some odd multiple of of pi by 2 will give me plus or minus 1. Okay, you find out those points, and you also find out the points where psi is 0. So then when x by A is, so when n pi x by A is some integer multiple of pi. And these 0 points are called nodes. So when you do this plotting, so let's do the ground state first. So for the ground state, you have, so for the point A by 2, if I put it here, so n is equal to 1, then there is 1 pi A by 2 by A. So that is just pi by 2, so 1. So there is 1 maximum at A by 2. Then if x is 0, of course you have 0, and when x is A, you have 0 as well. Are there any other points where it can be 0? No. So here you just have a function which goes like this. Fine. Okay. Now here I can tell you what would have happened if I had taken minus root 2 by A as A. Then you would simply have had the wave function go drawn in the opposite direction. But this doesn't really have any physical significance, because the physically relevant quantity is mod psi square, which will anyhow be positive. Okay, so whether it comes from a wave function that goes like this or it goes like this, it contains the same physical information. So, and it's sufficient to have only one of these cells. Okay. Then if we do the next one, so when n is 2, then if x is A by 2, then you have sine of pi, which is 0. So this point, middle point, now becomes a node. And if it's A by 4, you get a maxima, and if it's 3A by 4, you get a minima. So you get a curve like this. So you can reason out the other two as well, I am sure. So what you see is that as you move up in energy, the number of 0 points or nodes, it increases, and it has a linear relationship. So for a wave function with the quantum number n, the number of nodes is n minus 1. So there are 0 nodes here, 1 here, 2 here, 3 here. There is also the question of symmetry. So these wave functions can all be classified as either odd or even with respect to reflection about the middle point, a by 2. And you see that the ground state here is symmetric. It's the same. It has the reflection symmetry, so it's even. Then you have the second one, which is anti-symmetric, so it flips sign when you reflect it, and then the next one again is even, and then this one is again odd. Okay. So from a very simple model, so as soon as you had a confining potential, we got the sort of hallmark of quantum chemistry, which is the discretization of energy levels and also properties of wave functions. So this is just a sort of a warming up application that once you solve for the wave function, you get lots and lots of information. In fact, if you do a few exercises on particle in a one-dimensional box, you will see that you can use it in many, many ways and get a lot of insight into various aspects of solving the Schrodinger equation for whatever system of interest you want. Okay. So that is it for the class today. So next class, we will talk about how to do this for a particle which can move in 2 dimensions, let's say x and y. And also if instead of an infinite square well, we have a finite square well. And with that, we will also come to some new concepts in quantum chemistry, quantum mechanics, which you will learn about in many contexts later on. Okay, so I will finish now, and if you have questions, I can answer them, or otherwise I will just end the class. Okay. Oh, thank you, Archita, for the calendar, by the way. Are you maintaining it? Are some of you maintaining this calendar? No?
It was meant, I guess it's for the professors. Only professors can use it. Like
okay. But it was decided that people are not going to use it anyway. So the professors don't want to fill it in anyway. So it was suggested that maybe if the TAs want, then they can do it for their own class, and the professors can look at it. And then once the quiz is scheduled, you can sort of you can then update this quiz. So we are not really doing it. Okay. Anyway, stop presenting. Oh, thank you for whoever started recording. I forgot to start it. But I will close it now. Okay. Thank you.